Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 3 of these recorded sessions. Today we'll be going over for most of y'all Chapter 12 and in general oxidation reduction reactions, right? So as always, we'll be starting out with review questions and then towards the end we'll do um, review notes, summary notes, things like that to kind of cement it. So feel free to stick around for the review questions. As we do them, you can do them with me, you can do them by yourself, then see the discussion, or jump on over to the summary if you're just curious to what's being focused on, what's the main takeaway for this lesson, for this chapter, things like that. But yeah, other than that, you know, same format as always. So let's get started with our first question. And again, I'll give you guys plenty of time to pause. Hopefully, you guys try and do them yourself first, and then come back um, with the explanation if there are any, or if there needs to be any clarifications, things like that. So let's get started. So screenshot, take a picture, um, do what you want to do, you know, with these questions, and let's get started. So for the first one, you guys should have gotten the very obvious, right? We it's asking us what's not true about oxidation reduction, and we know reduction is actually a decrease in the Z bonds, right? So it's the opposite of what it was, and just kind of like to have our notes as we go. So this is kind of like, you know, as always, kind of like we're going through a test and you make notes on the side as you go. So this is so we don't forget down the line, right? So that's what we're gonna do. Oxidation, decrease of hydrogen bonds, right? Increase of oxygen bonds or Z bonds, right? Reduction, increase of H's, H bonds, decrease of O2 and Z bonds, right? So keep that in mind, especially, I mean, we are in chapter 12, oxidation reduction, literally, right? So now for two, you guys should have gotten what? A, right? Reduction. And why is it reduction? Again, why is it reduction? And let's do an explanation here. Why reduction and not elimination? So answer me that question. So you should have said in elimination, we gain pi bond, right? Or some sort of variation. We know back in OChem 1, elimination, we take out two sigma bonds and we gain one pi bond. So in here, we're not getting any pi bonds or anything, right? So it's not an elimination. And it's reduction because we just took out that CZ bond, right, which is the halogen. So that's all there is to it, nothing crazy. Three, you should have gone again, A, and same thing, right? It's not elimination because um, we didn't get a pi bond, right? No pi bond. And I guess I can add here a three as well. No, I'll just leave it like that. Okay, so four, what did you guys get? Again, this should have been also A because you guys might be thinking, well, we did get gain pi bond, right? Well, over here, let me redraw it. We lost two leaving groups, right? We lost two leaving groups. So if we lose two leaving groups, then we should have made two pi bonds, but we only made one pi bond, right? So if this was an actual elimination, so let's say elimination reaction, our product would have been just that, right? So just a triple bond with extra carbons on each side. So that's why it's not elimination once again, right? So again, as long as you know the concept of oxidation reduction, you're pretty much good to go, and you can use that for all the reactions following, right? Because same concept, And the only thing that kind of to watch out for, and you'll see later, is that again, stand anti, things like that, or what side do they prefer to attack? Is it backside, front side, things like that? That's kind of what you look for in these, because you guys know reactions start getting repetitive, things like that, and it's okay because that means less for you to worry about, less for you to memorize, work on, right? And just easier for you guys to um, study. So that's good. Win-win situation, right? Okay, five. You guys should have gone again. A. So far all reduction, right? And in this case, it's kind of obvious. For five, instead of gaining, um, or I mean losing a CZ bond, we actually lost an oxygen. So that's kind of more it's kind of more obvious in a way. And six, what do you guys get? Rank of increasing oxidation level. So for this one, you guys should have gone um, D, because once again, the easiest thing is to count those oxygens, right? So obviously, one has the most oxygen, so that's the most oxidation level, right? So that's all there is to that. And then from there, you count um, less oxygen, and then the most hydrogens, which is two has the most hydrogens, meaning it's the most reduced, so it's not oxidized, right? So anything to take away from that is this, right? So oxidation reduction, nothing too crazy. We just follow this, right? And we were good. So okay, so now let's go on to the next page. So again, pause, screenshot, take out your notes, do them, figure it out, and let's hear some explanations. Okay, so for seven, you guys should have gone C, and C again, oxidation level, right? So for the other one, for six, they were written out, but this time they're drawn. So same thing. Well, actually, it's also a different um order, but this time it's decreasing. But it's okay. Um, three is the most oxidized because of that double bonded oxygen, and then from there you decrease your oxygen level, and then your hydrogens come up, right? So the biggest thing for this, again, kind of paying attention to those oxygens because obviously oxidized. And then if you run out of oxygens, if there's no more oxygens on your molecules, then you pay attention to the hydrogens, right? Because the more hydrogens, the more reduced, and vice versa. So eight. Now we get to the reactions, right? Eight, you should have gone D, right? So the main takeaway for this is it is a reduction reaction, right? So PDC reduces. And in what fashion, right? So D, one or two, in the thin fashion. Thin. So now we're getting into that process, right? Okay. So nine is probably every semester is the most like questioned about question, I guess, um, because of heats of hydrogenation. And for this one, you should have gotten D. And this one's really simple once I do this, because heats of hydrogenation. So I'll do them here. Heat of hydrogenation. So, and there's a couple of this is not gonna apply to this, but um, it it'll make sense once we explain it, we talk about it. So more stable, as we know, is less energy, right? And then vice versa, less stable, more energy, things like that. And then for here, more crowded, what do you guys think? Less reactive, right? And we know that if there's a lot of steric hindrance, if it's just a lot of steric hindrance, density, things like that, it's going to be less reactive because the reagents isn't going to know where to go. So things like that. So this doesn't really, you know, apply to this question directly, but indirectly, what is it trying to say? It's trying to say that for adhesive hydrogenation, we care about stability and crowding, right? And for D, cannot be used to determine the relative stability. We don't care if they give different alkanes, right? That's not what it's about. This is about the stability and the crowdingness, right? Crowdedness. So we don't care if they give different alkanes because obviously they give different alkanes and they're totally different molecules, right? But for adhesive hydrogenation, we care about stability and crowded. And for A, B, and C, actually, you see how for A, they mentioned the crowding, right, with tri-substituted and mono-substituted. For B, they talked about E and Z, so stability, again, right? We know trans is much more stable, things like that. And then for C, um, well, same thing, trans and cis, right? Easy, things like that. So it's hydrogenation, no big deal, right? And you will get also asked about, you know, let's say, for instance, like another question between A and B, which one has the highest heat of hydrogenation? So now you look into stability and crowdedness, right? So the tri-substituted versus the mono-substituted, um, things like that. So keep in mind different ways to ask the same question, pretty much, right? So for 10, you guys should have gone D, right? So this one's a popular one, Lindler's, and it always reduces to double bond, right? So it doesn't reduce it all the way down to single bond. It's not that strong, but we know Lindler's reduces to double bond, and again, they have to be syn, right? Syn. You notice they're not trans. It's not E. It's Z, right? Syn. So nothing too crazy so far, right? Pretty mild. Um, yeah, and this is pretty much a theme for the next couple for the rest of the chapters because it's gonna be all reactions and it's just gonna be pretty straightforward. As long as you know the reaction, you're pretty much good, right? Okay, so let's go to the next page. And again, take a couple moments, pause the video, take your time, and let's see and let's compare answers. Okay, so for 11, Lindler's, we just talked about it, right? For 11, you guys should have gone D, right? We talked about um, how it reduces starting from an alkyne. So now you guys are probably thinking, well, this got reduced all the way down to a single bond. So what are you talking about? Well, this question has two reactions, right? So the first one is the Lindler's, and then the second one is the halogenation, the Br2, right? So Lindler's will take it all the way down to, let's see, it would have looked like this, right? A double bond. But now we take the Br2 right there and then halogenate it, then that's where we get reduce it some more and get the BRs over here, right? So there's two reactions in this one, right? So nothing too crazy. It's just they kind of trying to throw you for a loop by not putting the one and two, but don't get tricked by that. We know what halogenation is. That's like OChem one stuff, right? So okay, now for 12. So 12 is a good question because depending on your professor, they could get really tricky and very detailed or just very general, some professors like you to know every single step in a reaction, like what's the first step of this reaction, what's the second step of this reaction, what's the intermediate, or some of them are just very general, like this turns into this, you're good. But 12 is a good example of like what's happening in this reaction, like step by step. So this one, there's no trick to it. You either know it or you don't, but on your books and Learn Smart and all that jazz, you guys should have each reaction should have like a little summary, like, oh, this is step one, step two, things like that. So if you want to study that, skim through it. Pretty much, again, they get repetitive. So by the time you're through with a chapter, you're so familiar with it, like it's not even gonna take that much time to memorize all of it, or if anything, or you just pick up on it real quick because this involves addition. So obviously something's gonna add, and then something's gonna break, things like that. This involves elimination, so I know where things are going, things like that. So you'll catch on real quick. 13. So this one, which of the following products do not form? Right? Do not form is C, because we know MCPBA makes epoxides, right? That's like what they do. So 3 and 4 are not the products. 1 and 2 are actually the products. And that's the thing too with these questions that I'm giving you. Um, they're very, I guess should say, there's not a lot of them. There's only 20 per session per chapter that we're gonna do, right? But you can twist these questions around. You can rewrite them. You can rework them, reword them, right? Like for example, 13. What are the products? 1 and 2 are the products. So things like that. So take these as a good guide, and they're pretty good guides, right? If I say so myself, they're pretty good, and just twist them, or take out the answer choices and try to draw them out if you know, or try to write them down if you know, and then compare if what you wrote down is the right answers, things like that. So get creative. This isn't You guys are getting lots of good questions from these sessions because 20 per chapter. So each test, you'll have 60 good questions to kind of practice from, right? And they're all free, right? And they're all recorded, so you can keep coming back to them, so you won't have to lose them. And you know, just you can even print out copies once you screenshot these, so you can always have a fresh batch just in case you just want to go through them by yourself, right? So things like that. So study tips. So 14, you guys should have gone B, right? So, and in this question, which one could we have eliminated right away? A and D, right? A and D, because those are reducers, right? Um, so we should have been stuck with B and C. And in that case, again, with reactions, you need to know them, right? And we know OSO4 makes that syn alcohol, and that's it, right? Nothing too crazy, nothing fancy or complex about it. Yeah, that's all there is to it. And 15, ozonolysis is a good question. 03 um, is one of those questions that you're probably gonna see definitely because ozonolysis is very popular. So you guys should have gone for this one. D, and my trick for this one, we know ozonolysis cuts every double bond, right? Cuts every double bond and kind of just puts oxygen, oxidizes them on the ends. So what I like to do is, so we're given this, right? And then we ozonolyze it. So I like to do this, kind of elongate them, right, to separate them, and then put O's, and then everything stays the same. And then from there, you can kind of unravel it, right? So how many carbons do we have? 1, 2, 3, 4, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So, and we have a carbonyl on the second one, right? And then a carbonyl on the end. And this is the what number 4 is, right? So, yeah, that's kind of what I do. I unravel it after I cut it, right? So you don't miss a carbon, you don't miscount, things like that. So I think it's safer, personally. Okay, so let's go to the next page. Let me erase this. Okay, so we're almost done with this. So again, pause, screenshot, do, right? And then come back to me. Okay, so now for 16, this one's a good question as well. This is probably one of the types of questions you really want to understand because it might seem it's different from the previous questions we did, where it's just one reaction, right? This time it actually has two, things like that. So for 16, you guys should have gone B. And why is that? Well, what's happening in this reaction right now? So we're looking for the reactant. We have this and this, right? So what do we know this is? A base, right? That's a base. So what do we know bases tend to do? Bases tend to what? Substitute, eliminate, add. They tend to eliminate, right? So back in OChem 1, we talked about substitution SN1, SN2, E1, E2, and we know elimination deals with bases, strong or weak bases, bulky bases, things like that. And um, substitution deals with nucleophiles. So in this case, this is a good base, right? So obviously it's going to eliminate something to make that double bond, right? Oh, this isn't here. So, right. And then what do we know KMNO4 does with H2O OH? Makes that syn OH. So kind of connecting the dots, right? So nothing too crazy. You'll see this base used a lot, right, to make that double bond. So pay attention to those. Um, if it's not a specific reaction, a redox reaction, right, and it's kind of like, why are they using this? Well, just think: is it substitution? Is it a base? Is it elimination? What is it trying to make, right? And you can see from the choices, if we start with 1, how are you going to eliminate that pi bond, right? If you start with 3, we know OH is a bad leaving group, so that's not going to leave. And then we start with 4, we have an extra methyl, extra carbon right there at the end, which our product didn't have, right? So, yeah. 17, another ozonolysis. This one you guys should have gotten C. And again, we have this, right? And then where the double bonds over here. Again, cut them, right? Cut them. And then let's start with the top, the side, right? And then, oh, okay. So, right, those are our parts. And you notice that these two are the same. This is actually choice one, and this one is the second one, right? So our answer is C, 1 and 2. These are the same, so nothing too crazy. Now what happens? See, you see, even these practice questions, all ozonolysis, because it's the funnest one. It's the funnest one to do. 18. So what happens if we lyse a triple bond now, right? So you guys should have gotten A. Um, Instead of having two ends with carbonyls in triple bonds, it makes an alcohol in one of those ends, right? So nothing too crazy, and it's just one of those things that's like, okay, it's not an alkene, so obviously it's gonna do something, you know. So oxygenalysis is used for a lot of stuff. That's kind of like why it's good because it makes all these stuff. Now we have a carboxylic acid that we can use, right? So yeah, good deal, good deal. Okay, so let me go to the last page and once again, pause the video and tell me what you guys get. So for 19, you guys should have gone what? B, right? We know PCC is a reducer, right? Or actually, sorry, it's an oxidizer. Oxidizer. Oxidizer, right? But it can only oxidize once at a time. But this is saying we have excess, so we turn those OHs into carbonyls, right? And it's it. Nothing too special. You'll see PCC a lot as well. It's one of the common ones. One of the kind of just like, okay, I need a carbonyl. Let's use PCC, right? Okay. Now 20 is another you don't see this a lot, but it's just kind of there. It's fun, and you guys should have gone for this one, A, right? So we know negative DET, positive DET. So negative DET attacks above, from above, and then obviously from below. And that's all there is to it. So, and they make epoxides. So, epoxidation, oxidize, since I don't have room. Epoxidizes, right? So, flat attacks from the top, epoxide. Plus attacks from the bottom, epoxide, right? So, and that's why we chose A for this one, because it's coming towards us. That means it comes from the top, right? So, and this is one of those questions as well. Like, you can change up. What would the answer be if it was plus DET? B, right? And what reagent would it have been if our product was number 3? You guys could have used PCC, right? Because we talked about in 19 how PCC is just like makes carbonyls, right? So there's that, right? And again, as always, here's the answer key. But hopefully you went through it with me and you got the answers that way. But if you want to do this by yourself, you want the answer key on hand, so you don't have to keep going back to the videos. Feel free to screenshot this, print it, do whatever you want. So now let's close this up and do our little summary. And this summary is not gonna touch upon every single little thing, right? It's gonna touch upon um, the main stuff, the good stuff. Like we don't want the fluff, right? So first, we're gonna touch upon reduction. Reduction. So we know reduction is minus O2 plus H's, right? We don't takes away the O's, we add the H's, things like that. And what reduces? So we have metal catalyst, and we saw that with palladium, right? Palladium, ET, nickel, and actually later you'll see how some of these are stronger than the other ones, right? So what other things reduces? Alkali metals. So pretty much a lot of metals, like we didn't see before, right? Alkali metals and NH3. And then third set is going to be our H, obviously, right? H is plus or minus with boron and aluminum. So these are kind of grouped this way because these are the best to kind of like worst, most to least, I guess. But I mean, either way, they produce, right? Aluminum. Okay, so now we go into the actual reactions, like the specific reactions. So for this first one, we have something that's called catalytic hydrogenation. So from the name itself, catalytic hydrogenation, obviously we're just hydrogen, right? Hydrogenation, hydrogenation. Okay, so with that, it's gonna be the 2H2 plus PDC. So, and we saw that in the practice, right? PDC, so nothing crazy. And this one reduces to, and I'll do it here, reduce to a single bond, all the way to a single bond. Reduce to single bond. Okay, hopefully I have enough room. I should. And then we have the Lindlers, catalyst. Catalyst, this one's always the easiest one because it has a familiar name, right? Lindlers, and you'll see this a lot. Lindlers everywhere, right? So Lindlers and syn H2, so you're gonna add H2 in syn fashion, right? Which makes sense. Pretty much just reducing it. Um, we have the dissolving metal reduction. So dissolving metal reduction is gonna be NaNH3, and this is anti H2. So Lindler's kind of opposite of Lindler's. Anti H2, right? So these are kind of opposite from each other. And then we have epoxides. Epoxide, position opening. So LiAlH4. This one you'll see a lot, time and time again. So OH. So it makes an OH in an SN2 fashion. And then there's another one that's called um, alkyl halide reduction, and same thing, LiAlH4, right? And this turns into just RH, right? RH. So these are the reactions, and let me color some of them in just to kind of like make them pop, right? So we have catalytic hydrogenation, makes this. Linders makes turns into syn H2. We have NaNH3 that's anti-H2, and then our epoxide opening, it opens it from SN2 fashion, so backside, and the primary, hopefully primary alkyl halide, and then we have the RH over here, which is no big deal, right? So yeah, pretty much the same. You've seen all these play out before, but now they have a name, right? Okay, so now let's go to oxidation. And this one has a little bit more, so we're probably going to use 2 pages. Oxidation. Okay, so oxidation, again, it's plus O2, right, minus hydrogen. So we have, again, the types of oxidizers. We have O to O2 bonds, right? Obviously, lots of oxygens there. So O2s, O3s, H2O2, um, CH3, COOH, peroxy acids. We'll see this later. Peroxy acids, RCO3H, composed like that, right? Okay. So, and then we have again metals, right? And you kind of see obviously oxidation, just look up for lots of hydrogen, of oxygen somewhere. So metal O2 bonds. So these don't have as better of a names as reduction, but so over here pretty much chromium and then Na2, chromium again, 2O2. We have K2Cr2, um, O7. I don't have room. O7. Okay. And then these over here are strong, non-selective, non-selective. So they don't care, right? They're strong. They're gonna oxidize whatever they want. They're gonna oxidize everywhere. And then we have our weak ones. PCC is selective, and then we have KMNO4. We saw this before. This is probably the most common ones. It's just there. It's just it oxidizes. We don't really care too much about it. OSO4, Ag2O. Right. So out of that, PCC is selective. Right. So yeah, lots of examples, and these are pretty much what you'll see oxidation-wise. So you don't gotta worry, because as long as you have these, if you're familiar with them, just straight away, especially with the chromiums. Chromiums are a dead giveaway, right? Chromiums. So now, with that being said, let's go to a new page and do the actual reactions. Oxidation. So we have epoxidation right away. Epoxidation, which we use peroxy acids. Peroxy acids are used, so peroxy acids, and again, they're composed of RCO3H, right? And this turns into syn addition, right? And MCPBA is a good peroxy acid. MCPBA is a good one. And then now we have dihydroxylation. Sorry. Dihydroxylation, right? So there's two parts to this. Again, epoxidation. And then we have when we use another, there's no name for it, but another reagent. So epoxidation is we're gonna be using OH minus or H3O plus, which will lead into syn OH. And then we have, if we use KMNO4 or OSO4, is going to be anti-OH, right? Anti-OH. So pay attention to that, right? Syn, let me add this one, epoxide, just to kind of, okay. Now ozonolysis, we know ozonolysis is O3, so we have internal and terminal. So internal, we make carboxylic acid. So times 2 carb acids, right? So, and then with terminal, we make carboxylic acid and a CO2. So carb acid plus CO2. So yeah, and we kind of saw that earlier with the carboxylic acid, right? So last but not least, alcohols. So if we're dealing with alcohols, we have primary, and hopefully this will fit, primary, and if we use PCC on primary alcohols, we will get aldehydes. And if we use CrO3 we'll get carboxylic acid. Now we have secondary, and if we use for secondaries, we can only use CrO3, and we get for that ketone, or actually CrO3 or PCC. Sorry, let me erase this. Okay, so we can use both. Both of them, both PCC and CrO3 will yield the same um, product. So PCC will just make into ketone. And for these, you don't have to kind of memorize them, right? Because they'll make sense and things like that. So with that being said, that's all I have for you guys. And these two reactions is very important. And again, you know, feel free to kind of take what I've written down and rewrite them yourself. Definitely should. Don't just screenshot them because they're messy. But definitely reword them, color them in, and put them in a little index card even, and try to write all of that info in there. And there's not a lot. Most of them are repetitive, so yeah, why not, right? And start making your list of reactions because you're gonna do it for the final anyway. So we'll start now. And yep, that's all I have for you guys. If you guys have any questions regarding the questions, um, obviously ask your professors or your SI if you have one. And other than that, that's all I have. So thank you guys for watching, and hopefully that helped. Thank you guys.